Okay, here we have our free body diagrams for question number 1. I've dismantled the link into two different paths, A to B. This link A to B with uniformly distributed load here, and B to C where it is pin jointed here at C and at B. So here we have 0,5 meters, and here 0,5 meters, and here 0,5 meters, and here our uniformly distributed load is at 1.25 kilo newtons per meter. So what we do here, if we consider this first part, we put our moments our reaction RAV here and RAH here, and then we put on at C we have RCV in that direction, and then we have the horizontal reaction which is RCH, and likewise at point B we have RBV which is on the vertical, and we also have RBH which is on the horizontal. And then we can consider this point again on point B of this second link. We have our RBH, and then we have this vertical moment, our RBV. So this RBV is equal to this RBV, but now for the sake of direction according to Newton's third law of motion, our RBV, this one, will be pointing downwards. For every action there is an opposite reaction. Then we have our two equations that we need to derive for this, and then two equations also for this. So we'll start with the force equation. If we add our forces vertically, we have RAV plus RBV being equal to the resultant force due to the uniformly distributed load, which is 1.25 multiplied by, this is 1.5, and it will be acting at the center for the center of mass from, so 1.5 divided by 2 is times 0.75. Then we can call this one our equation 1. Then we look at the moment equation. The moment equation, we can say the summation of moments about point A is equal to 0, taking all clockwise moments to be positive and anti-clockwise moments to be negative. So here we can have minus RBV multiplied by 1.5 plus 1.25 times 1.5 times 0.7 being equal to 0. This 0.75 being equal to 0. This will give us our RBV being equal to 0.9375 kilonewtons. Now, if we take equation, this one can be equation 2. If we take equation 1, we can say now RAV plus 0.9375 is equal to 1.25 multiplied by 1.5 multiplied by 0.75. This will give our RAV being equal to 0.9375 kilonewtons. Now we need to get the reactions again, RCV as well as RBH, and RBV we now have it, we only change the direction. So here what we can do, we can now come to point C, and on point C we can say the summation of all the forces in the vertical direction is equal to 0. This will give us now RCV minus RBV being equal to 0. But remember, we have our RBV from this equation. This will give us our RCV being equal to 0.9375 kilonewtons. Now we have this reaction, the RCV. Now we take moments about point C. The summation of moments at C, taking the clockwise moments to be positive, is equal to 0. Now we can say minus RBH multiplied by 2. Remember, we have 2 meters here, minus RBV multiplied by 1.5 is equal to 0. So RBH is equal to minus 0.7031 kilonewtons. Then we take summation of all the forces in the x direction is equal to 0. If we take that moment here, we can say RBH minus RCH is equal to 0. This will imply that RCH is equal to minus 0.7031 kilonewtons. So here, this is where we are with the working so far. I'm flipping over to the next page. Summation of the forces in the x at point C is equal to 0, which will give me RAH minus RBH being equal to 0. Then if we come to this presentation now, we now have our RAV, RBH, but still here we have our RAH that we need to calculate. So RAH minus RBH should give us 0. So here we can get our RAH being equal to minus 0.7031 kilonewtons. Now if we draw our UDL, here we have our RAH, which is equal to minus 0.7031, and then we have our reaction here, which is equal to 0.9375, and then here this is our point A, and then we have our point D here, and we have our uniformly distributed load, which is equal to 0.625 kilonewtons. Remember, it's acting on the center of the A to this point that we have cut here, where we have our normal force at D, and then we have our reaction here, thus D, and then we have our moment here in this direction, which is MD, like this. We can now have our equations, the summation of the forces in the x being equal to 0, which implies that here we can calculate minus ND plus 0.7031 is equal to 0, which implies that ND is equal to 0.7031. Then we can also do the summation of the forces in the y direction being equal to 0. We can have our VD plus 0.9375 minus 0.625 being equal to 0. So our VD is equal to minus 0.3125 kilonewtons. Then we can now say the summation of the moments at D is equal to 0, whilst we are taking the clockwise moments to be positive. Here we can get 0.9375 multiplied by 0.5 minus 0.625 multiplied by 0.25 minus MD being equal to 0. Our moment at D is equal to 0.3125 kilonewton meters, since it is a moment. So we have our VD here being equal to minus 0.1325, and we have our ND. Our ND, we calculated it here, it's equal to 0.7031 kilonewtons, and then our MD is here 0.3215 kilonewtons. So here we can do the other part. Now let me write here where it is a little bit legible, and on this part we can say we have our NE, and then we have our moment ME. These are the same with the ones that we have calculated from above, and here we have our UDL. Its effect is here 0.625 kilonewtons, and the distance here is now at 0.5 meters, and here at point B, this is point E, and then this is point B. We have here our reaction force RBH. We have calculated it to be 0.7031, and then on RBV, this is RBV, we calculated it to be 0.9375 kilonewtons. Then here we now have our VE at that point. Our VE, we are yet to know it, and then we have our NE, we are yet to know it, and then we have our ME, which we are yet to determine. Let me flip over to the next page. Right, summation of forces in the X is equal to 0. Then our NE minus 0.7031 is equal to 0, which implies that my NE is equal to 0.7031 kilonewtons. Then the summation of the forces in the Y is equal to 0, which implies that my VE plus 0.9375 minus 0.625 is equal to 0. So here my VE will give me 0.3125 kilonewtons. Right, then we got the summation of moments at point E, taking clockwise moments to be positive, is equal to 0. This will give me my ME plus 0.7031 0.625 multiplied by 0.25 minus 0.9375 multiplied by 0.5 should give me 0. This implies that my ME is equal to 0.3125 kilonewton meter. So I now have the forces as well as the moments, the normal force and the moments at point E. This is where we are now. Let me come to the inclined part now. We have this free body diagram, and then we have cut out E. F is now at this point, and we have C, and then here we have RCV, which we have calculated to be 0.9375 kilonewtons, and then we have this reaction force RCH, which is equal to minus 0.7031 kilonewtons. Then using the SOHCAHTOA, we have our 53.13 degrees here, and we have our VF, and then here we have our NF, and in a similar way we have our MF here. So we can take our summation of moments about point F, taking the clockwise moments to be positive, to be equal to 0. So we can have our MF minus 0.9375 multiplied by, here our moment from this point to, our distance from this point to that point is 0.6 meters. So we can now say this one multiplied by 0.6 minus 0.7031 multiplied by 0.8 being equal to 0. My 0.8 is from this point down to that point. Using the triangle, this is 0.8 meters. So the summation of moments about point C, taking this one to be positive, is equal to 0. We can now have our VF, this VF multiplied by 1 plus 0 being equal to 0. Therefore, VF is equal to 0. If we come here, we can use our similar triangles. You remember the Z triangles. We can have here this angle being equal to 53.13. It's similar to this angle. And if we take here, we can still have our angle here 53.13. So we can say the summation of forces in the x direction is equal to 0, which implies that NF minus 0.7031, then we take the cosine of 53.13 plus 0.9375 sine 53.13 is equal to 0. This implies that my NF is equal to minus 1.17 kilonewtons. So here we now have the N, this, and we have our MF, here. So this is what we have. We've managed to get our, this is NF, our NF, our VF, and MF. So that's the story.